In fact, this is the somehow continuation of my talk that I gave a year ago in previous conference. And at that time, we were just starting. We constructed, and I gave the motivation of why we were using the algebras that we were using, and how we thought things would work out. Today, I will talk more about mathematical properties of these systems, and if time permits, then I will speak a little about its application in the new system. But I will mainly focus on this characterization of this variety and the logical systems as well. So again, this project is the collaboration between the biologists of Tbilisi State University and the logicians from interdisciplinary department. And the main objective, I will repeat some of the slides from last year. So the main objective is to characterize biological systems, specifically immune systems and its cells, by means of relational systems. And we are using we use mathematical tools to somehow for diagnosing the states or for make some forecast about the future state of this system. And mainly we'll consider the T cells, the so-called T cells, which are part of the system, and they are clever cells that possess some knowledge about their own states and about the states of the cells that they communicate with. And the interpretation we were using, so the distinction was that the notion of quasi-knowledge. The agent box Q is the agent quasi-knows proposition alpha. And as the basis of the logic we were using, we constructed the logic corresponding to the Chang's algebra. So we'll start from MV algebras. Strangely, I'm the first one, I think, that for these 2 days that mentions these algebras. So if someone doesn't know, here's the definition. So the main example is, of course, 0-1 segment, and I will go some of the slides a little faster because this part is already on YouTube for multi-billion viewers, and the main motivation why we choose this algebra is because it has the elements which are called infinitesimals. And these infinitesimals have distinct properties. They are not, which form the radical of the algebras that we are considering. And here is the Chang algebra itself. So it is the totally ordered, it's a chain where we have practically the two sets of this. And here the operations are defined in the. So these operations are given by this algorithm. We will use it in the next slides. So this algebra actually is the smallest MV algebra that has the infinitesimal points. So its infinitesimal points are the ones that no matter if we take point x, no matter how many times we'll multiply it by itself, we will not get 0. So usually on this usual algebra 0-1, therefore 0-1 segment, which is which defines the variety of MV algebras, doesn't have this property, but the C does. And actually, the C algebra is a subalgebra of is generated by its radical, and every perfect algebra, a non-simple MB algebra, contains copy as a subalgebra. And yeah, I'll do so about this property, which gives us the tools to characterize the notion of quasi-true. And so quasi-true values are exactly coinfinitesimals, and quasi-false values are infinitesimals. So when we will be evaluating the stuff, we'll have this in mind. Algebraically, to fix the algebras, we take MV algebras, then we take monadic MV algebras, where we have operators for quantifiers, and plus we have another axiom that gives us the final axiomatization of what I considered algebras. So this is the axiom that actually gives us the perfect MV algebra. So the subclass of these algebras that have infinitesimals. On logical side, we start with Lukasiewicz logic. Of course, add the modality of operator box Q with appropriate inference rules, and of course, additional axiom for analogous to the perfect axiom. And thus we obtain logic ELP. So it's, of course, it's not surprising that this MFVC algebras are the algebraic counterparts of ELP. So it's by construction, it's how it was how it meant to be. Is how it's meant to be. So this is a small introduction about what are the algebras and what logic do we consider, and the main problems and actually the new part, the talk or the new results will be about the unification in these varieties, unification in this logic, the process of the notion and of unification, equational unification, of admissibility rules, and so on. Just to fix the terminology, here we have, so by PM we take a set of propositional variables, and by PM all propositional formulas. If we take into consideration equivalences, then we get Lindenbaum algebra. So we can write PM for the free algebra and PM as the set of its generators. The substitution is substitution sigma is just we can substitute in a formula every occurrence of the variable. We can substitute by a formula, and we can following way. And the substitutions, for these substitutions, we can define more general and less general substitutions in the following manner. And we are mainly, of course, interested in the substitutions that make the formula theorem, and these are called unifiers. And the set of unifiers can be the set of unifiers for the formula alpha is a quasi-ordered set, and if we take such an equivalence relation, then get poset from that. We need this because the main question is so how many and of course we are looking for the best solutions or the best, most general unifiers. So the question arises, so how many most general unifiers can there be? And depending on the type of the logic or the, the classification is different. Here I've only given the definition for the unitary unification type, which means that if every solvable unification problem alpha, it's exactly one most general unifier for the alpha. And to tackle this problem of how to describe and get the unification type of this system, we use the E-unification or equational unification techniques. And the relevant definitions and techniques were introduced by Silvio Bardi. And here the algebraic unification problem is finding for a finite presented algebra, we have to find a pair PU such that P is a projective algebra and homomorphism from A to P. And same as it was in the logic, so set of unifiers of A. Yes, here we can define the more general and less general unifiers in a similar way. So if we have one unifier and then we say that U is more general than W, if there's a homomorphism G is such that W is equal to G composition GU. And the set of algebraic unifiers of presented algebra forms a quasi-ordered set, it's quasi-ordering, and the unification type is defined in a similar manner as it was for the logic. So description of the algebraic E-unification goes through the notion of projective algebras and finitely presented algebras. So here is the definition of projective algebra. If someone doesn't know, they are basically the retracts of the free algebra. As about finitely presented algebra is an algebra which is generated by finitely many generators, and there are finite number of equations that holds on these generators. And if there is any other algebra with the same properties, then we have a homomorphism sending these generators into these generators. So again, if for any set, if we generate a monadic filter by the set X, it will have the same this property. So it will be all the elements which are greater than or equal to this combination of elements. So here's what we got. If P is an Emery term, then there is a principal monadic filter such that these two algebras are isomorphic. As a corollary, we have that if an algebra, MVC algebra, is finitely presented, then there exists a principal monadic filter such that this factor algebra is isomorphic to this finitely presented algebra. On the other hand, if we take an element in this free algebra which is not an infinitesimal and generate the proper principal monadic filter in free algebra, then there exists some Emery term P such that again these two algebras will be isomorphic. So combining the two propositions, we will have that an M-generated algebra is finitely presented if and only if there exists a monadic filter such that this factor algebra is victorious. So the finitely presented algebras are exactly the factor algebras of the free algebra. And as a relation between projective and finitely presented algebras, such a result that M-generated algebra is projective if and only if it is finitely presented and it's isomorphic. It has a one copy of Chang's algebra as a multiple in the multiple case. So it can be presented as Z times. So here C is what it gives us using this technique, we can show that the unification type of the equation of class MLBC is unitary. And reformulated in logical words, the unification type of the logic ELP is also unitary. And this gives us the, so every formula, or unifiable formula, has exactly one most general solution. We'll come back to so the set of formulas of ELP is recursively enumerable. Set of axioms is recursively enumerable. So the set of theorems of the logic ELP is also recursively enumerable, and as the universe of this algebra is recursive set and operations are defined algorithmically, these algebras are recursive. And using this criterion of decidability of the logic, we can obtain ELP is decidable because it is recursively axiomatizable and characterized by recursive. Now about admissible rules, I will skip the definitions. I'm sure all this, and we can make the evaluation of the formulas of EFP in natural way. Just slate proposition of formulas into terms and then keep it. Then keep the values of the formulas, construct the formulas by the values of the appropriate terms. And the valuations, we satisfy the formula if it satisfies the rule. Having said either way alpha and gamma or this one. So it's a usual natural evaluation, and we say that the rule is valid, will satisfied by every evaluation. And conversely, the validity of the open formulas can be reduced to the validity of rules, as the formulas can be expressed in conjunctive normal form for each cause that will give us the disjunctive notion of atomic formulas, and then that such a cause that this formula is valid in A and only if it's. So here we just take the formula P and the projective normal form and just chop it apart. So what we have is a rule is valid in all MVVC algebras if and only if it is derivable in ELP. Also, the following are equivalent, that the rule is admissible, it is valid in all three algebras, and it is valid in all three algebras or finite sets. And we can show that admissibility of the rule in the logic ELP is decided. Now, a little bit again about the system of Arduino system. So we construct the Kripke frames using this algebra, and Kripke model is constructed the standard way. The difference is that we have in the evaluation, we have the notion of we take another clause that if EP or omega is in negation of the radical, then this property should be kept in all the successors of the points. We'll say that the formula is modally valid, where if it is evaluated one in all Kripke frames, and moreover, we have the notion of quasi-validity. In this case, evaluation goes to the negation of the radical, and the same for one satisfiability. This is so we have that any theorem of the logic ELP is modally valid, and any modally valid formula of the ELP is accepted. So now a little bit about how we try to use this these algebras in in biology. So there are a lot of types of cells which have really this kind of relations. Just one of the schematic relations that can be represented, and we try to represent immune system as the set of T cells and with some actions between them, and identify T cell with an agent and an action between T cells with a relation between agents. So we represent this the immune system as a C-level descriptive Kripke frame, and we have the notion of activation and quasi-activation. So cells, and so we will say that cell is activated, state is activated if the evaluation is 1. Quasi-activated, it's negation of the radical. Then we have an epistemic state function that I have spoke about this more extensively. Skip this to and for the newer part. So what can we obtain, and how we went a little bit further during this last months. So the one use of this new method will be such. So we can experimentally establish some concrete, first of all, the sentence, say 5, valid for the current state of the system, immune system, and we'll try to construct a propositional formula corresponding to this sentence, and then we can argue, say, and what formulas will be the consequence. Psi will be consequences of phi. And in the medical words, what kind of properties can we deduce from the current state? And if we speak more precisely in mathematical ways, is this rule admissible or not? So this way we can somehow predict, can we or cannot predict the future state of the system. Another way is that suppose we have again some state of the system, and this state can be represented by some formula phi, and the conditions for which this state is achieved can act as a unifier of then the biological question is, what measures do we need to take to achieve this state? And according a more precise mathematical question will be what is the unifier of phi? So these are the rough sketches of how are we trying to use these methods, and how to try to use these mathematical tools to understand the real life problems. So it's basically it. Thank you.
Any comments, questions, remarks?